All right, let's talk about one of the most important yet almost completely invisible technologies that keeps our modern world running. It's called automatic control. It's the silent force behind literally everything from your air conditioner to massive industrial plants. And we're about to pull back the curtain and see how it all works. I mean, seriously, think about it. You just set your speed, and the car, well, it just holds it. It doesn't lurch or lag when you start climbing a hill. That smoothness feels like magic, right? But it's not magic at all. It's a perfect example of control engineering, and we're going to use it to understand exactly how these systems think. So let's dive right into that exact scenario. We'll call it the constant cruise control problem. Honestly, it's the perfect way to break down the core challenges that all of these control systems are designed to solve. Okay, so here's the fundamental issue. That uphill slope, an engineer would call that a disturbance. It's an outside force that's trying to mess with our system. Without some kind of controller, your car would naturally slow down going up and speed up going down. So the mission is pretty clear. Build a system that can fight these disturbances all on its own. The first and probably the most intuitive way to solve this is with something called feedback control. It's a really simple and totally reactive way to solve a problem. The logic here is just so straightforward. The system is constantly asking itself three simple questions. 1, how fast are we going right now? 2, is that the speed we want to be going? And 3, if not, what do I do to fix it? It just measures, compares, and then corrects. This little loop runs over and over and over, constantly tweaking the throttle to get rid of any error. And that's the formal definition right there. It's all about looking at the result, the output, and then feeding that information back to the input to shrink the error. The most important thing to get here is that it only acts based on the effect of a disturbance. And this, right here, this highlights feedback's real superpower, robustness. You see, the system doesn't need to know why the car is slowing down. It could be a hill, a crazy headwind, maybe even a tire going flat. It doesn't care. It only sees one thing, the error, that drop in speed, and it acts to fix it. This is what makes it so incredibly reliable. And here's what that looks like in a proper engineering diagram. Now, don't let the boxes scare you. Just follow that main loop along the bottom path. You can see the output is measured, and then it's fed all the way back to be compared with the speed we want. That constant loop is the absolute heart of feedback control. Always watching, always reacting. But there's a catch. Of course there's a catch. For feedback to do anything, an error has to happen first. The car actually has to start slowing down before the system can do anything about it. So it's always playing catch-up. Now, for a lot of things, that's totally fine. But what if we could be faster? What if we could be predictive? And this brings us to a much more advanced strategy, feed-forward control. This is the proactive, predictive fix that we were just talking about. This is the million-dollar question. What if our car had a sensor, I don't know, maybe a GPS with terrain data, or some forward-looking scanner that could actually detect the hill coming up? What if the system knew about the disturbance before it even had a chance to affect our speed? And that's the whole idea behind feed-forward. Instead of measuring the output, which is the speed, it measures the disturbance itself, the hill. It then calculates the exact amount of extra gas needed to cancel out that hill, and applies it before the car even has a chance to slow down. It's preemptive. So let's put them side by side. Feedback is reactive. It feels the car slowing down and then hits the gas. Feed forward is predictive. It sees the hill coming and hits the gas before anything happens. One gives you that rock-solid robustness, the other gives you pure speed. But feed forward has its own fatal flaw. It is not robust at all. It can only handle the specific problems it's been designed to look for. So yeah, it can handle the hill, but it has no idea what to do about that sudden headwind we talked about. It's incredibly fast, but it's also fragile. And that's why you basically never see it used all by itself. So if one is robust and the other is fast, what's the logical next step? Well, you combine them, of course. This is where we get to create a system that truly has the best of both worlds. And here it is, the full picture. Let's look at our diagram again, but now you can see both paths are working together. The feed-forward controller, that's the top path. It sees the disturbance and makes that fast, preemptive move. It does all the heavy lifting. And meanwhile, our trusty feedback loop down at the bottom is still there, just cleaning up any tiny little errors that might get through, like from that unmeasured headwind. And this is the main takeaway. They cover for each other's weaknesses perfectly. Feed forward makes the big, fast, predictive move against problems we know are coming. Feedback follows right behind it, making sure everything is exactly on target and safe from the unknown. It's a beautiful partnership. Okay, so combining feedback and feed forward gets us a near perfect system. But what about really complex situations where the inputs themselves are unstable? For that, we need a pro-level technique called cascade control. The easiest way to think about it is that we're basically introducing middle management into our system. Just imagine a main manager, that's the outer loop. Its only job is to watch the big picture goal, like the final temperature of a product. Now, instead of controlling the heater directly, this manager gives a command to a worker, the inner loop, and says, hey, I need the steam pressure to be exactly X. The worker's only job is to maintain that steam pressure, quickly fighting off any little fluctuations before they ever have a chance to affect the final temperature. The manager manages the worker, and the worker manages the process. But there is one golden rule for any of this to work. The inner loop, our worker, has to be way faster than the outer loop. That worker needs to be able to solve a dozen small problems in the time it takes the manager to even realize something might be slightly off. Okay, so we've got feedback, feed forward, and cascade in our toolbox. Let's see how these all come together to run some really critical pieces of industrial equipment. Okay, let's look at a power plant boiler. The number one goal is to keep the water level perfectly stable. That's the main job for our feedback controller. The biggest disturbance is how much steam is being pulled out, so a feed-forward controller watches that and predicts when we're going to need more water. And finally, the flow of that incoming water can be a bit unstable, so a super-fast cascade controller's only job is to keep that input flow rock steady. You've got all three strategies working together in perfect harmony. And we see the exact same pattern in something like a heat exchanger. The final temperature of the fluid is the big goal. That's handled by feedback. Any changes in the fluid coming in are the main disturbance, so that's handled by feed forward. And the steam used for the heating? Well, its pressure can fluctuate. And those fluctuations are quickly stamped out by a dedicated cascade loop. It is just an elegant and incredibly effective design. From the thermostat on your wall to the massive systems running our power grids and our factories, these principles, feedback, feed forward, and cascade, are literally everywhere. They are the silent, tireless guardians that keep our world in balance. So the next time things are running just a little too smoothly, you might just have an elegant control system to thank. What do you think it is?